Welcome students again. So let's discuss the flow through a circular tube using equations of motion. Okay, we already derived the profiles using momentum shell balance. Okay, so here we are going to use the equation of motion. Okay, once we use the equation of motion, we will see that we will arrive with the same profiles. Okay, so we don't have to take a thickness around anymore, but okay. So the thing is, first make the assumptions, right? Flow through circular pipe. Okay. So what are the assumptions? Write down the assumptions. It is same as before. Incompressible flow, rho is constant, right? You write incompressible flow, right? Then you can write it is steady state, no change with time, steady state flow. Then you have, fully developed flow. Fully developed flow means what? The direction of flow is not changing in the direction, right? If the fluid is flowing in this direction, so it will not be a function of this direction. Okay. Then again you can have the yes, rho is constant, mu is constant, that is viscosity is constant. 5 newtons, Newtonian fluid, you are assuming Newtonian fluid, so it will obey the Newton's law. Okay, what else are there? Then okay, then the flow profile, right? So you have to use the coordinate system, right? So according to the problem, if you see the problem here, so you are using cylindrical coordinates, right? So you have to fix this system. Okay, you can take in this direction also, but the definitions will be different, how you define that modified pressure. Okay, only so stick with this example. So this is R, this is Z. So fluid is flowing in Z direction, so Vz is not equal to 0. Since it is a fully developed flow, it is not a function of Z in this direction, but Vz will be a function of radial direction, right? That's how momentum gets transferred. So it will be in direction of R. What about VR? VR is 0. There is no flow in the radial outward direction or radial inward direction, right? What is V theta? There is no rotation of fluid, right? So there will be no fluid in the theta direction. Okay, 0. Okay, what about pressure? Pressure is a function of Z, right? Fluid is flowing in a downward direction because of the fluid pressure, right? Is there gravity? Yes. So what are the components? Gx, there is no, gr, there will be no gravity component in radial direction because we don't have a centrifuge, right? There is no centrifugal force acting here. So we'll have 0. What is the gravity in Z direction? That is Z. Or is the gravity in the theta direction? 0. Right? Okay. So with this, now we can use the equation of motion. Okay. So first we have to solve the equation of continuity. So now you have to use this one, right? Cylinder coordinate system. This one. So solve it. So incompressible flow, rho is constant, 0, because you are getting derivative with the respect to time. Or you can say it is steady state also. And here there is no flow in the radial direction. So this VR is 0. The whole term will be 0. Here again there is no flow in the theta direction, no rotation. So 0. Vz, yeah, the Vz, there is a flow in the Z direction. But it is not a function of Z. So if you take the derivative, it will be 0. So from continuity equation, you didn't get anything. Okay. Now next solve the equation of motion. This was Cartesian coordinate. We already solved it for falling film. Now we'll go for cylindrical coordinates because we are solving in cylindrical coordinate system. Okay. So we have to go through each component. So in first, we'll go through r direction. Okay. So steady state, no change with time, 0. Also rho is constant, right? So it has taken out. Then VR, then again this term will be 0. So all VR terms will be 0. VR 0. This is V theta, right? There is V theta is also 0 because there is no rotation, 0. Pressure, there is no change, pressure gradient in the radial direction, 0. Again, tau r will be a function of VR, right? So VR is 0, so whole thing will be 0. Again, this will be, VR will be involved, so this will be 0. Again, there is VR term, so 0. Right? Tau theta theta also include V theta, which is 0. There is no gravity in radial direction, 0. Okay. So you can also try putting the, see the Newton's law of viscosity for the cylindrical coordinates. Okay. So yeah, cylindrical coordinates. Tau r, say it is a function of VR, right? This is again 0 because it is an incompressible, right? Incompressible, this is definitely 0. So this is the VR is 0. So tau r is 0. You can also take this one, tau zr, right? So what is tau zr? So that is Vz, but this will be there. But in here, where was that? Okay. Right? Everything is 0 now. Okay. Again, solve for in the theta direction. No, steady state 0. P theta is 0. Also VR is 0. The whole term will be 0. P theta is 0 again, 0. P theta is 0. So 0. V theta is 0. VR is 0. 0. There is no change in pressure in the theta direction, 0. Tau r theta will involve V theta, which is again 0. Again, this will involve P theta, 0. Again, this is theta, right? So V theta 0. Again, this will be 0. There is no gravity in the theta or no component of gravity in the theta, 0. Okay, only we are left with this term. So steady state, this will be 0. VR is 0, so whole term will be 0. V theta is 0, the whole term will be 0. Vz is not 0, but Vz is not a function of z. So if you take the derivative, this will be 0. So whole term will be 0. There is a pressure is there, this will not be 0. Again, there will be tau r z because this will give you dou Vz by dou r. So Vz is a function of r, so this will be there. This is not 0. Again, this will have your, so you can see the theta z and zz you have to see, right? So okay, so if you see theta z, right, so it is a Vz, right? Vz is not 0, but it is not a function of theta, so 0. V theta is 0, right? So this term will be 0. Then again zz, so if you see the zz, this will be 0 because it is incompressible flow. Vz is not a function of z, so this is 0. So only the term left will be these two terms, right? So you can write it down. So if you write it down, so you have 0 equal to minus dou p by dou z. Then you have minus 1 by r dou by dou r tau rz. Yes. Okay. Now you can integrate it. Okay, gravity will be also there. Yeah, this gravity will be there. So it is nothing but rho g. So plus rho g. Okay. So you can rearrange this term. So dou p by dou z minus rho g equal to minus 1 by r dou by dou r Okay, so now you can integrate this equation. So this, we have two variables here. So what we'll do is, definitely tau r z is not a function of z, right? So you can integrate separately. However, you can directly put dou p by dou z will be, definitely this is the pressure gradient in the z direction, right? This is nothing but it will be equal to p minus, or the pressure at the above top one, p naught minus p by l, the length of the pipe, right? Okay, so you can easily put it here. The gradient will be same. Okay, so if you put it here, so it will get p naught minus p by l, right? Now you can use the definition of modified pressure, right? You have done before. Okay, so if you use the modified pressure, p naught minus rho g 0, right? It will be again 0 only. There is nothing. And minus p at PL, at the bottom point, minus rho g L. Okay, and you can divide by L. Right. So this is your modified pressure. This is nothing but the capital P naught minus P L by L. Okay, so you can put it here instead of this. We have written in the terms of modified pressure. So you can recall it, right? Modified pressure was P plus capital P is equal to P plus rho G H, right? It was plus sign, but because our coordinate system is in this direction, that's why it is minus here. Okay, so you can check the earlier videos why it is minus. Okay, so if you write it here, so it is nothing but capital P naught minus capital P L by L. Okay, how you can integrate this equation? Right, so if you integrate this equation, you'll get the same as earlier. So if you check it, so you have got this one. See, if you rearrange that equation, you'll get this, right? Again, just integrate and divide by r on the both sides. Okay. Again, same boundary condition will be used at r is equal to 0, because at the center there is no wall, right? So shear stress is always 0 at, or finite at the center or away from the wall. So this is finite. So if you put r is equal to 0, then the tau rz becomes infinite, right? So this is not possible. So C1 has to be 0. So C1 goes out, so only you're left with this. So you have got this, right? Now you have to put the Newton's law in this formula. So Newton's law is this one only, right? You just put it and integrate it. You'll get this. Apply the boundary condition. Vz is 0 at r is equal to capital R, radius of the cylinder, right? So if you put it here, you will get this one. Okay, other factors, it is same as done before, right? So you can integrate it, you will get it. So we are solving the problems using equation of motion, right? So we came to the third problem, flow through annulus, right? We derived this equation using momentum shell balance, right? Now we are going to derive the same, formulas using the equation of motion. Okay, so this is similar to as the flow through a circular pipe. Okay, only the difference is the boundary conditions. Okay, kappa r, lambda, I already told you. Okay, So only change in the boundary conditions. Okay, this is almost same as the flow through a circular pipe. Also here the coordinate system is in this direction. Okay, so you can take here also, but choose the coordinate system wisely so that it makes things simple. Okay, and you can use the same steps as before. Okay, I will give you this problem as a homework. Okay, so you have to solve this flow through endless problem using equation of motion, following all the steps. So how to solve it? I already told you. You have to write the assumptions, right? All the assumptions. Then in which direction there will be velocity, in which direction it will be zero, right? Then you have to derive, first solve the continuity equation. If it gives you some equation, then go for the cylindrical coordinates equation of motion. Okay, solve it. Then use the Newton's law to use to get the velocity profile. Okay. 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 I will leave it as a homework. I will post it in the Google Classroom. Okay. Thank you.